we will find the exact area under a graph on a given interval AB. To do so, we need very small subintervals, which means that n is very, very large. The width of each rectangle is always the total length over n, which is delta x, which equals to b minus a over n. For the best refined subdivision, the width is the limit when delta x approaching 0, which means that this is the limit of n approaches infinity of b minus a over n. Recall, when the width of each rectangle was large, we had to choose the height from several possibilities, for example, the left endpoint, the right endpoint, or the midpoint. You can see here, look at the yellow part here, that this is one possibility, and this is another possibility. This is like the midpoint. When the width of each rectangle is very small, it's zero width. Then the left endpoint and the right endpoint and the midpoints are all identical. When the width of each rectangle is zero width, any point in the interval can be used as a representative for the height. We write x star for this point, so the height of the rectangle is f of x star. Let's now try to set up an integral for the exact area by doing the Riemann sum. The area of each rectangle is the height times the width. The height is f of x star and the width is delta x. Again, x star is any value of x in the specific subinterval. We call x star a sample point. X sub I star is the sample point in the ith subinterval. The total area is the sum of these areas. So first we are going to sum the values of the f of the x stars, because all the rectangles have the same width, so I can distribute the delta x, but then I will have to take the limit of n approaches infinity. In short, we can use the sigma notation, and we get that the total exact area is the limit when n approaches infinity of sigma when I runs from 1 to n of f x sub I star delta x. Now we will replace delta x by b minus a over n, so you can see that there is something there that has to do with this n. But this is a constant with respect to I, so I can take it out of the sigma. Because, again, the sigma is with respect to I can take the b minus a to the n out of the sigma, but I should leave it after the limit, because it contains n and the limit is related to n. And I get this. Or another way of writing this is as limit n approaches infinity of delta x times the sigma of f x sub I star when I runs from 1 to n. Here is our first example. Find the exact area under the curve y equals 1 plus x to the power of 2 on the interval 0, 1. We will start with the subdivision of the interval 0, 1. The width, which is delta x, is b minus a over n. In this case, we get 1 over n. Here's the first segment, and the second, and then so forth, and here's the last one. And then we need to pick the x sub I star, these subintervals. And we know that the total area is the limit when n approaches infinity of 1 over n, because this is the width, and we have to sum the heights, and the heights of each one of those rectangles, it's going to be the value of the function at the chosen x sub I star. But I can do much more here. I know that the function here is 1 plus x to the power of 2. So I'm going to replace x sub I star by the actual value of this. X star can be any point in a subinterval, which means that it is okay to choose the right endpoint. I need to keep everything very organized, so I don't want to choose a different x stars in each one of the subinterval, so it's really good to choose every time the same one. In this case, in each one of these subintervals, I'm going to choose the x star to be the right endpoint. So now I need a new picture here. In the first subintervals, I'm going to choose 1 over n. In the second, I'm going to choose 2 over n, and so forth. And in the last one, it's n over n or 1. Now I'm going to replace all the x sub I stars. The first one, as you can see, is 1 over n. So I'm going to replace x sub 1 star with 1 over n. The second one is the right endpoint of the second subinterval. It is 2 over n, and so forth. And the last one is 1, but to keep the pattern here, I will write n over n, not 1. Now I need to work out the summation, and then to take the limit. Let's start with the summation. First of all, I see that I have all these ones. Because it's only addition, we can really commute and compute this sum in any order that we like. So we like first of all to add all the ones and then to add all the other. Now we have to evaluate this sum. Let's start with a 1 plus 1 plus 1. We know that each one of the subintervals is contributing 1 plus 1. And because we have n subintervals, we have 1 plus 1 plus 1 n times. And this sum is n. Now we have to work the second one. We pay attention and we see that all the yellow part is something over n to the power of 2. So the first thing to do is to distribute 1 over n to the power of 2. And we get this. Now we have to work this sum of 1 to the power of 2 plus 2 to the power of 2 plus so forth plus n to the power of 2. But for this we have a closed formula. We know that this is n times n plus 1 times 2n plus 1 over 6. And we get that. Now we are going to multiply the bracket by 1 over n. The first one is 1, and the second one is n times n plus 1 times 2n plus 1 over 6n cubed. The limit of 1 when n approaches infinity is 1. So I can just rewrite it like this. Now we have to find the limit of this rational function when n approaches infinity. This is very easy. There are many methods to apply here. What I'm doing now is dividing everything by n cubed, because the highest exponent of n in the denominator is 3. And I know that this is approaching 0 and also this one. And I get 2 over 6. So everything is 1 plus 2 over 6, which is 1 plus 1/3. And I get 4 over 3. I conclude then that the total area under the curve on 0, 1 is 4/3. Now we would like to use the sigma notation. With the sigma notation, the top one can be written as such. This is a shortcut of the summation from the left. But now, because I know what is the function is 1 plus x to the power of 2. And also I decided to take my representative point to be the right endpoint of each of the subintervals. I am going now to replace f of xi star by 1 plus I over n to the power of 2. I'm using a property of the sigma here. I'm using the linearity. First, I break it to two sums. The one is the sums of the ones, and the second is the sum of the I n to the power of 2. But n to the power of 2 is not dependent on I, so I can actually distribute n to the power of 2. In the summation of I, 1 over n to the power of 2 is a constant. Now I really have to evaluate each one of these. And now actually we are coming back to what we did before. We know that the first sum is n and the second one is this one. And we just continue exactly as before. Let's now see in parallel the same problem without the sigma notation and with the sigma notation. This is exactly the same, obviously. And this is exactly the same, expressed as just plus plus and expressed using the sigma notation. And this one. From here, as you can see, both are exactly the same because now it's about taking the limits and arranging the algebra, but we don't have anymore the sigmas because we're already replacing the sigmas by some expression of n. We are ready for the precise definition of the definite integral. Let f be a continuous function on an interval ab, which is divided into n subintervals, each of length delta x equals b minus a over n. Let x sub I star be a sample point in the ith subinterval x sub I minus 1, x sub I. Then the limit n approaches infinity, sigma runs from 1 to n of f of x sub I star delta x is the definite integral of f from a to b. We write the integral fx dx from a to b. In short, we conclude that the integral between a and b fx dx equals limit n approaches infinity of the sum I runs from 1 to n of f of x sub I star delta x. Now we can understand better the definition for the definite integral. Just pay attention that before we were talking about areas and functions that were always above the x-axis or on the x-axis, never below the x-axis. But this definition is also going to work very nicely even if the function is positive, negative, or 0.